Hi folks, welcome back to Physics with Captain Rod. The purpose of this video here is to demonstrate how to calculate the electric field due to a ring of charge. So, I'm working on my picture here as best I can. Let me kind of describe it to you. So imagine here for the time being that we have this ring of charge right here, this thing. And we're going to imagine it's got a total charge Q. It has a radius R, which we're going to imagine our constant for this example. Now I put in a coordinate system here in X, Y, Z coordinate system. So imagine that this ring is in the XY plane and makes a right angle to the x-axis. And what we're going to try to find here is the electric field at this location as it varies with x, x being this distance in this problem. So, first, you have to realize that, this is a cylindrical type of problem. If we look at this from like this viewpoint, basically what we're going to see, I'm going to move this over to here. I'm going to do some messing with the geometry here. From that viewpoint, what we would see is a circle. Our charge distribution would look like this. And the radius, would be this distance here. Now, the z-axis in this picture might look something like this. The y-axis straight up, and the x-axis is coming right out at us. All right, now, as far as how we're going to handle this, and the answer is we're going to handle it just like we handled the previous problems. We're going to break this charge distribution into little chunks. So imagine kind of a chunk of charge here. Now, the first thing you realize is that chunk has a charge, which I'm going to give a name. I'm going to call that dq. In my picture over on the left, that chunk might look something like this. All right, left, over on the right. Now, the charge density. I can get the charge density by taking the total charge. Now, in the previous video, what I did is divided by the length, because the charge was spread out over the length. It's spread out over a length here, except that length is a circular circumference. So I'm going to go ahead and put 2 pi r in the bottom. So Q over 2 pi r gives me the charge density of this ring. Now, to get the charge, we need to take the charge density and multiply by the distance. Now, what you have to realize about this problem, that distance right there, basically that I circled, that's not a dx or a dy. That's a little arc length. Usually we use s to measure arc length, so that's equal to ds. Whoops, not d theta, ds. Come on, erase. There we go. That's equal to ds, which is equal to r d theta. That comes from basically definition of a radian. In this picture, not the greatest picture, but there's my d theta and there's my r, right? So the ds is equal to r d theta. So if we take q and divide by 2 pi r, multiply by r d theta, we now have what I would call dq, charge on that element. And you'll notice that the r's divide out, which is perfectly fine. Okay, now we're going to draw the electric field vector at P due to this element. Now what you need to realize is that electric field vector points directly away from that element. So in this picture, it might look something like this. I'm going to go ahead and label it DE. Here's an angle, let me call it alpha, be the same as this angle in this picture. Now, the tough part is really understanding that vector. That vector is not in the XY plane. This is a three-dimensional problem. That vector basically is pointing kind of back into the screen, so to speak. And that's important to realize as we move on with this. Right? Now, another thing to consider. From the symmetry of the problem, we know that the net field is going to be in the x direction. So we don't need to worry about the y component or z component or any other component of that electric field other than the x component. So other than the x component. This picture right here, if I draw the components, let me do those in blue. Okay, so DEX, DE, I'm just going to put perpendicular x. It's not really a DEY because, again, you got to look at the 3 dimensions of this. That's just the component perpendicular to x. It could be a DEY if this thing were aligned perfectly. Like if this point right here were right there on the y-axis, then it would be a DEY. But all other points, it's not. All we need to worry about is this one, because we know that the net field is going to be in the x direction. So when we calculate the electric field, right, dE x direction is going to equal k dq, which we already found over here. dq is equal to q over 2 pi d theta. So there's our k dq over distance squared, or over r squared. In my picture, the distance we need is this distance from here to here. Now, if we were to look maybe from like this viewpoint here, I can draw a little triangle. I'm going to draw that triangle right here. This is the angle I have labeled alpha. This distance is x. This distance is r, the radius of our charge distribution. So the distance we need is this guy, which is equal to the square root of x squared plus r squared. Now, getting back to this equation over here, this was kq over r squared. So by the time we square this, the radical goes away. We can just put x squared plus r squared. Right? Now, remember, we need just the x component. I don't think I need this triangle anymore. We need just the x component, so I'm going to multiply by cosine alpha. Taking note over here, that's the same angle alpha. I guess I did need that picture, but that's okay. Cosine alpha from that previous picture is equal to x over r, and r was equal to square root x squared plus big R squared. So there's our expression for the net electric field. Now, it's kind of a complex looking expression, but there's some good news coming here that I'll be able to give you in a minute. Let me get this line written out. Total electric field, we're going to have to integrate this. And I'm going to go ahead and pull the constants out in front right now. K, Q over 2 pi can all come out in front. In fact, I'm going to need more room for the constants. K, Q over 2 pi. But further inspection here, let's think about this. X is not a variable of integration. As far as the integral is concerned, x is a constant because x is that distance, and that distance isn't changing as our point moves around this circle, through the integration process. So for the integral, that distance is constant, which means that x can come out in front. And let's see, r also constant. Heck, this whole kit and caboodle can come out in front. So out in front of this integral, x squared plus r squared. And when we take x squared plus r squared times x squared plus r squared to the 1/2, we get x squared plus r squared to the 3/2. Integral d theta. That's the only thing there that's varying, is the theta. Everything else is constant. Integral on theta, well, we're just going to run theta from 0 to 2 pi. And we end up with really going from what was looking like a very complex math expression, but by the time you bring out in front everything that's constant, theta is the only thing varying in that equation. When you integrate d theta 0 to 2 pi, you get 2 pi. And that's going to cancel this 2 pi. So what we end up with is kqx over x squared plus r squared to the 3/2. There is an expression for the net electric field at this point right there, as it varies with x. Now again, checking it, I always recommend doing our checks. Check number 1. The thing, your electric field expression should always have units of kq over distance squared, and it does. Check number 2, if this point were a long way away, and that means mathematically if x is a lot bigger than r, then the electric field should be approximately equal to kq over x squared. And it's pretty easy to show when we look at this expression. Imagine x squared a lot bigger than r squared. You can lop that off. This thing simplifies to kq over x squared. We're good to go. So there's our expression for the electric field. If you don't mind, I'm going to go back here and try to make that part of the picture a little better after the fact. But boom, boom, there's the ds, there's the d theta, that's r and r. So anyway, I hope this video helped demonstrate how to find the electric field due to a ring of charge. Now there's, in addition to the calculation we just done, what we now know, now that we have an expression for the electric field due to a ring of charge, in problems coming up, what we're going to do is we're going to take that expression, and sometimes we'll take a charge distribution and divide it up into maybe rings of charge instead of little chunks of charge. And because this is the electric field due to a charged ring, we can use this expression to write an equation for a ring of charge and integrate to get maybe some sort of surface of charge. And I'll be making an example of that video next. So anyway, have a great day.